Let's start our next section, which will be 11.3, which is about the dot product of two vectors. So let's start with a definition of what the dot product is. The dot product of two vectors, I'm just going to use two-dimensional vectors right now, u1 and u2, and a second vector v, v1, v2 is, so the way we denote a dot product is by a dot, u dot v, and what you do is you multiply the first entries together, u1, v1, plus u2, v2. Now, one important thing to note is that when you take a dot product, the dot product produces a scalar. This is the sum of two numbers, so you no longer have a vector anymore. It's just a number in the end. And how would we define the dot product if our vectors were three-dimensional? So if your vector u1, u2, u3, and if v had three entries, v1, v2, v3, then your dot product would be u1, v1, plus u2, v2, plus u3, v3. So now that we know what the dot product is, let's talk about some properties of the dot product. So the first one is the dot product is commutative. So if I take u dot v, it's the same thing as v dot u. Because this dot product is defined in terms of multiplication and addition, we get that it's commutative. The second property is that if I take u dotted with a sum, u plus v, you can essentially distribute u dot v plus u dot w. Number 3, if I take a scalar multiple, if I multiply a scalar and a dot product, it's the same thing as scalar multiplication on u dotted with v, or it's also the same thing as u dotted with the scalar multiple of v. If I take the dot product of the zero vector with any other vector, you get 0. And the last one is that if I take the dot product of a vector with itself, you get the magnitude of the vector squared. So let's look at a problem where we're computing some of these dot products. So let's say my vector u is going to be 2, negative 2. My vector v is going to be 5, 8. And the vector w is negative 4, 3. And I want you to compute the following. So let's start off with u dot v. So take 2, negative 2, dotted with 5, 8. We get 2 times 5 plus negative 2 times 8. 10 minus 16, we get negative 6. And again, if we look at our answer is just a scalar, a number. It's no longer a vector anymore. Okay, let's compute now u dot v with w. Now first, I will tell you, let's look at what kind of answer we're going to get. So here I have the dot product, which is a scalar. So I have a scalar multiple of a vector. So in the end, my answer should be a vector here. Okay, so let's compute this. Well, we already computed this dot product in the last part. So this would be negative 6 scalar multiple with w, which is negative 4, 3. So I'm getting positive 24 and minus 18. Okay, now let's compute u dotted with 2v. Again, I'm taking a dot product here. My answer should just be a scalar, not a vector. So here, this is the same thing. We can use our properties up above. Use property 3. This is the same thing as 2 times the dot product of u and v, which we already computed to be negative 6. So 2 times negative 6 is negative 12. There's my answer. Let's do one last one. D. It's the magnitude of w squared. Well, if we want to compute this, property number 5 tells me this is the same thing as the dot product of w with itself. So the dot product of negative 4, 3 with negative 4, 3. So 6, so here I'm getting negative 4 times negative 4 plus 3 times 3, 16 plus 9, or 25. And here your answer will always be positive when you take a vector dotted with itself, because if you look here, magnitude or length, remember that's a positive measurement, and you're squaring it, so it'll stay positive.